Let me tell you something that nobody in the movie business wants you to know. The space between us and the nearest star is not a backdrop. It is not a setting. It is not a stage waiting for brave human actors to stride across it with their laser rifles and their shiny boots. It is a physical object. It has properties. And when you study those properties honestly, with nothing but mathematics and a willingness to be uncomfortable, the thing you discover is not inspiring in the usual cinematic way. It is something far stranger and far more interesting. It is a wall, an absolute physical, mathematical wall built from the deepest architecture of our universe itself. People love the story. You know the one. Humanity builds a magnificent ship, fires up some beautiful blue engine, and 4.3 light years later, some brave crew steps out onto alien soil and plants a flag for the species. It is a wonderful story. I enjoy it as much as anyone. But if you are actually curious, if you actually want to know what the cosmos is made of and what it will and will not allow, you have to be willing to throw that story away completely. Because the physics of getting to Alpha Centauri is not a story about engineering. It is not a story about courage or willpower or the indomitable human spirit. It is a story about energy and mass and the unfeeling geometry of space-time, and those things do not negotiate. The distance alone is almost comically hostile to the idea, 4.3 light years. People say that number and it slides right off them because they have no intuition for it, and frankly, neither do I when I just hear the words. So let us make it physical. Light travels at roughly 186,000 miles every single second. In 1 year, light covers about 5.9 trillion miles. Multiply that by 4.3. And you get 25.3 trillion miles. That is the distance to the nearest star, not the nearest interesting star, not the nearest star with planets worth visiting, just the nearest star, period. The closest neighbor we have in this enormous, mostly empty galaxy. Now, our fastest spacecraft ever launched, the Voyager probes, travel at roughly 38,000 miles per hour. If you pointed a Voyager probe at Alpha Centauri today, it would arrive in roughly 73,000 years. A human civilization lived and died and left no lasting trace multiple times over in 73,000 years. So chemical rockets, the kind we actually know how to build, the kind burning kerosene or liquid hydrogen with an oxygen oxidizer, are simply not part of the conversation. They are automobiles being asked to cross an ocean. We need to think about something much faster. And the moment we do, the universe introduces us to three physical nightmares that stack on top of each other like a cruel cosmic joke. The first nightmare has a name that physicists like me find darkly amusing. We call it the tyranny of the rocket equation, and it is a tyranny in the most literal sense of the word. It is an equation that rules over every rocket that has ever been built or ever will be built, and it does not allow exceptions or workarounds or clever engineering tricks. The rocket equation was written down by a Russian schoolteacher named Konstantin Tsiolkovsky in the late 1800s, and what it says, in the plainest physical terms, is this. The only way to accelerate a rocket is to throw mass out the back of it. Every pound of thrust requires burning propellant and ejecting it at high velocity. The faster you can eject that propellant, the more efficient your rocket is. But here is the brutal part. The fuel itself has mass, and that mass has to be accelerated along with your payload, which means you need fuel to accelerate your fuel, and then you need fuel to accelerate the fuel that accelerates your fuel. The equation is exponential. It grows catastrophically fast. If you want to get a spacecraft to 1/10 the speed of light, which is still an absolutely crawling pace that would take 43 years to reach Alpha Centauri, the math becomes genuinely disturbing. Using the very best chemical propellants we have, where the exhaust velocity is roughly 4.5 kilometers per second, the ratio of fuel mass to payload mass becomes so enormous that the number itself is practically meaningless. The fuel required would outweigh the payload by a factor that has more zeros in it than you can fit comfortably on a page. We are not talking about needing a big rocket. We are talking about needing a rocket so absurdly massive compared to its payload that building it is physically indistinguishable from building a small moon of pure propellant and lighting it on fire. People say, well, what about nuclear propulsion? What about ion drives? What about solar sails? And yes, these things improve the efficiency dramatically. A nuclear pulse drive or a fusion rocket can achieve exhaust velocities thousands of times higher than chemical rockets, and that does incredible things to the fuel-mass ratio. But it does not eliminate the exponential penalty. It merely moves it to a less insane range of numbers. And there is the additional complication that we do not actually know how to build a fusion rocket. We do not have controlled, sustained fusion power on Earth at all. We are being asked to build a fusion engine that works reliably for decades in the hostile environment of deep space when we cannot yet build one that works for 5 minutes in a laboratory. But say we solve all of that. Say some future generation of engineers cracks the fusion problem and builds a ship that can genuinely push itself to a meaningful fraction of the speed of light. Say 20% of c, a speed at which you could reach Alpha Centauri in about 22 years. Now you are no longer fighting the rocket equation alone. Now you have made an appointment with Albert Einstein, and he has some deeply uncomfortable news about what happens to mass and energy when you start moving that fast. This is the second nightmare, and it is a beautiful one in the way that all true things are beautiful, even when they are terrible. When you move at low speeds, the kind of speeds that Galileo or Newton or any classical physicist thought about, your mass is just your mass. It is a fixed number. It does not change when you speed up. But Einstein showed us something extraordinary. He showed us that energy and mass are the same thing written in different notation. The equation is the famous one. And what it tells us in the context of motion is that kinetic energy does not just add to the motion of an object. At relativistic speeds, it adds to the effective inertia of that object. It becomes harder and harder to accelerate the faster you go. Not because of friction or air resistance or any ordinary mechanical reason, but because the geometry of space-time itself is pushing back against you. As you approach the speed of light, the energy you need to accelerate by any additional amount grows without bound. Specifically, it grows toward infinity. There is no engine, no fuel, no physical process in the universe that can push a ship with non-zero mass to exactly the speed of light, because doing so would require an infinite amount of energy. The speed of light is not a speed limit in the engineering sense, the way that a car has a speed limit because its engine is not strong enough. It is a speed limit in the geometric sense. It is baked into the structure of space and time at a level so fundamental that asking what would happen if you exceeded it is like asking what happens north of the North Pole. The question does not have an answer because the premise is physically incoherent. Now, some people hear this and they say, well, what about time dilation? And this is where the physics gets genuinely astonishing in a way that I find personally delightful. It is true that a ship moving at a large fraction of the speed of light will experience time differently than observers back on Earth. If you push a ship to 90% of the speed of light, time on that ship runs at roughly 44% of the rate it runs on Earth. At 99% of the speed of light, time on the ship is running at about 14% of Earth time. This means that the travelers on board experience far fewer years than the people they left behind. A journey that takes decades by Earth reckoning might feel like only years to the crew. But here is the thing about time dilation that the movie industry conveniently forgets. The Earth years still pass. When the crew of that ship arrives at Alpha Centauri and sends a message home, their families and friends and everyone they knew has aged the full duration of the journey as measured in Earth time. And when they return, if they return, they step off a ship into a world that has changed by decades or centuries while they personally experienced only years. Time dilation is not a shortcut. It is not a cheat code that lets you visit the stars casually. It is a profoundly strange feature of reality that makes relativistic travel deeply, philosophically alien to anything a human being would recognize as normal life. And we still have not gotten to the third nightmare. This one is my favorite, not because it is the most fundamental, but because it is the most viscerally physical, the most immediate, the most genuinely lethal in a way that engineering cannot solve by just building something stronger. Imagine you are driving a sports car made entirely of glass through a sandstorm, not a gentle sandstorm, a violently churning sandstorm with winds so powerful that individual grains of sand hit the glass like bullets. Now, imagine you are doing this at 1,000,000 miles an hour. The grains of sand are the same grains of sand. The car is the same car. But the kinetic energy of each impact has increased by an enormous factor because kinetic energy scales with the square of velocity. Grains that were irritating at normal speeds become lethal projectiles at 1,000,000 miles an hour. That is a rough and honest picture of what interstellar space does to a relativistic spacecraft. The interstellar medium is not empty. I want to be very precise about this because popular accounts often get it wrong in ways that matter. Space is not nothing. Between the stars, the average density of matter is about 1 hydrogen atom per cubic centimeter. That sounds like nothing. It sounds like less than nothing. It sounds like the most extreme vacuum you could possibly imagine, and by ordinary earthly standards, it is. But now consider a spaceship moving at 20% of the speed of light. That ship has a cross-sectional area, say 10 meters by 10 meters, 100 square meters. In 1 second, that ship sweeps through a column of space roughly 60,000 kilometers long. At 1 hydrogen atom per cubic centimeter, that is an enormous number of hydrogen atoms hitting the nose of the ship every single second. At 20% of the speed of light, each of those hydrogen atoms carries the energy equivalent of a fast proton in a particle accelerator. They are not gently bouncing off the hull. They are penetrating it. They are ionizing whatever material they hit. They are generating secondary radiation, a shower of gamma rays and energetic secondary particles that propagate through the hull and into the interior of the ship. The biological crew inside is being irradiated not from outside the ship, but from inside the hull material itself, which has been turned into a source of lethal secondary radiation by the incoming particle flux. The dose rates at these velocities are not manageable with ordinary shielding. You might think, well, make the hull thicker. But thicker hull material means more mass, and more mass means more fuel required, and we already established that the fuel requirements are exponential. More importantly, thicker shielding does not always help with high-energy particles. There is a well-known effect in radiation physics where very dense shielding can actually increase secondary radiation at certain energies. The problem is not simple, and the solution is not simply more material. There is also the question of the interstellar dust itself. Grains of dust in the interstellar medium range from nanometer scale to micrometer scale, tiny fragments of carbon and silica left over from ancient stellar processes. At low speeds, these are inconsequential. At 20% of the speed of light, a single micrometer grain of silica carries the kinetic energy of roughly a small explosive charge. Not a nuclear weapon, but genuinely comparable to a shaped charge that engineers use to cut through steel. Now consider that the ship encounters many such grains over a journey of 22 years. Each impact erodes material from the hull, vaporizes it, creates a crater, ejects secondary particles. The cumulative erosion over an interstellar journey at relativistic speeds would eat through any foreseeable material before the ship arrived. Various engineering proposals exist. Magnetic scoops to deflect incoming ions, laser systems to vaporize dust grains ahead of the ship, sacrificial ablative shields at the nose. Each of these proposals has its own energy cost, its own mass cost, its own cascade of engineering problems, and none of them has been demonstrated to work at the scales required. They are ideas. Good ideas, some of them, but ideas and working engineering solutions are separated by a distance that in some fields is greater than the distance between us and Alpha Centauri. Now, I want to say something important here because I have been painting a very dark picture, and I mean it sincerely and honestly, but I do not want you to walk away from this with a sense of despair or defeat, because that would be a misunderstanding of what the physics is actually telling us. What the physics is telling us is not that the universe is cruel. It is not trying to keep us trapped. It is showing us something much more interesting than that. It is showing us the actual scale of things, the actual honest, measured scale of the universe we live in. And that scale is so enormous, so absolutely uncompromising in its enormousness, that our ordinary human intuitions are simply not equipped to hold it. The rocket equation is not a failure of human ingenuity. It is a precise, beautiful description of how mass and momentum actually work. The relativistic mass increase is not a punishment. It is the consequence of the most elegant and deeply verified physical theory we have ever constructed. The lethal flux of interstellar protons at relativistic speeds is not the universe being hostile. It is just kinetic energy being kinetic energy, following the same rules that make a baseball hurt when it hits you, scaled up by the remorseless mathematics of high velocity. There is something I think is genuinely more thrilling about this honest picture than about any science fiction fantasy. The fantasy gives you the stars easily, and in doing so, it accidentally makes them small. It makes them destinations you can casually hop between like cities on a train network, but the real universe is something far more extraordinary than that. It is a place where the nearest star is so far away that the most energetic physical processes we know of are barely adequate to begin to contemplate reaching it, where the fabric of space-time itself enforces a speed limit by making mass infinite at the boundary, where the very act of moving fast enough to cover cosmic distances turns the near vacuum of space into a lethal radiation environment. That is not a depressing picture. That is the most dramatic picture of physical reality I have ever encountered. It means that the tiny, warm, improbable blue planet where we live is not just one stop among many on some galactic route map. It is an island. A genuine island separated from the nearest other island by an ocean so vast and so physically hostile to crossing that the ocean is not merely a distance but a fundamental property of how space, time, energy, and mass are organized at the deepest level. And there is something about knowing that, really knowing it, that changes how you feel about the night sky. Those stars are not close. They are not neighbors in any sense that the word neighbor normally implies. They are other worlds at distances so extreme that the laws of physics as we understand them do not obviously permit us to visit them, and yet we can see them. We can measure them with such precision that we know the surface temperatures of their photospheres, the composition of their atmospheres, the orbital periods of their planets. We have done all of that without going anywhere. We have done it from this one small rock by building instruments and applying mathematics and being genuinely, rigorously curious about what is actually there. That is worth something. That is worth an enormous amount, actually. The fact that a conscious species evolved on this planet and then figured out, through nothing but careful observation and honest reasoning, that the nearest star is 4.3 light years away and has a surface temperature of about 5,000 Kelvin and orbits a binary partner with a period of about 80 years, that is one of the most remarkable things that has ever happened in the history of matter, arranging itself into interesting configurations. And you do not need to go to Alpha Centauri to participate in that. You need to be curious. You need to be honest about what the mathematics actually says rather than what you wish it said. You need to be willing to sit with the uncomfortable fact that some distances are genuinely, physically, permanently enormous and find that fact fascinating rather than discouraging. Because the universe did not promise to be convenient, it did not promise